An ambulance has a siren that emits sound of a constant frequency. The ambulance is moving directly towards a stationary observer. The ambulance decelerates, so it's slowing down as it is approaching the observer, and then accelerates after it has passed the observer. How does the frequency of the sound heard by the observer change as the ambulance is approaching and as it is moving further away from the observer? All right, so let's think about while it's approaching. As it is approaching, here we have an observer, and here is an ambulance that is about to run him over. So it wants to slow down, right? So it's moving this way. So it has some velocity at this point, and let's say once it gets over here, it'll have some velocity, right? So it'll be lower because over here, because it is decelerating. So over here, so the observed frequency will be higher because of the Doppler effect, because it's approaching it, but it's approaching, and the faster it approaches you, the higher the effect of the Doppler effect, right? So over here, the speed is high, then over here, speed is low. What's going to happen to the observed frequency? So over here, he's hearing it slightly higher than the car, but right now when the ambulance gets over here, the frequency will still be higher, but it'll be less than before because the velocity has decreased. It has slowed down, right? It's much, much lesser, probably. I'm assuming it's close to a stop. So it's going to be much less. So what's happening to the frequency? It's high, then it's low because it's decelerating. So that's not to confuse ourselves that the original, it's not, compared to the original frequency, at both times you're experiencing higher frequency as it gets closer, but it's going to be really high when the speed is really fast, and it's going to slow, it's going to decrease as the ambulance slows down. So the frequency as it approaches will decrease. And the reverse will be true because as it is moving away, did I say approach away? As it goes further away, the observer is over here, and it's going to accelerate. So right now he's going to hear a lower sound of a lower frequency. So it's over here, but it has some velocity, which is low. And as the ambulance moves further away, now the frequency, the velocity is much, much higher. So over here, the Doppler effect would be much higher. So what's going to happen to the sound? What's he going to observe or feel or listen to? So over here, he'll listen to a lower sound, which as he moves further away will also decrease. I was actually thinking about increase. So as he moves further and further away, the sound, the note will become lower and lower. So yeah, so it's going to decrease because the car is speeding up away from him. So it's going to decrease away. Interesting. I was actually expecting it to go the other way. So we have decrease and decrease. The correct answer is then A. Which wave behavior is shown in the diagram? So over here, we have there's a wall in the middle, maybe some sort of rise or an actual wall, and the water is coming through, and we see the waves actually spreading out as they go through this area. So we've seen that a lot. Well, not too often, but once we end in the chapter, when a wave is coming in and it hits an aperture which is small, close to the wavelength of the wave passing through it starts spreading out like that. And this is exactly what we're seeing, and this is called diffraction of the wave. A mobile phone battery is charged by connecting it to a constant potential difference of 5 volts. After a time of 1 hour, the initial current of 0.5 ampere slowly decreases to 0. So it's charging for the first hour, then it slowly charges for the second hour. Some cell phones do that to protect the battery. If it charges too fast, too quick, that just ruins the battery over time. It just causes stress on the battery. So over time, so this is like most charging cycles. You've probably noticed when you're charging your phone, first, maybe not an hour, but like first 20 minutes, it just goes from 0 to 50. Then it takes another hour to go from, or maybe even longer, from 50 to 100, right? So this is more of a real life example. Okay. They're asking for what is the best estimate for the energy transfer to the battery. So we know the current, but we can't just apply P equals to VI to figure out the power because the voltage is constant, but the current is not. So what would a power graph look like? No, understanding that the voltage over here is constant and the only thing varying is the current. So if I try to draw a graph that would tell me the power, it would look a lot like this. The power given to the cell phone. So practically the exact graph that we have over here. So the height would be the power, and we can calculate it by VI. Over here, the initial, the current will be 0.5 and voltage, well, it's constant. That's going to be there. So the maximum value will be here, and it's going down, but it's going down the same gradient as it is over here. So this is more or less highlighting the power curve for the same battery, where we see the current curve over here, right? So once we know that, it becomes really easy. So let's just, take it a step further. I'll just erase this and I'll just use the same logic over here. I'll say this is actually my power graph and power versus time in hours. And okay, I didn't realize this was hours, so now we know, so that's good. And so what is this value now? That's going to be 0.5 times 5. So that should come out to be, this should actually be 2.5 watts, right? And this is the time. How much is the first time in seconds? This is going to be 3600, right? Actually, I want to figure out the area. So instead of putting that over here, I know this distance is 3600 and this distance is now 3600. So, and I know the height is 2.5, and of course the area under this graph is giving me the energy, the total energy transferred into the cell phone. So let's calculate that real quick. Right, so the area is 9,000 joules, right? And the area over here, I don't even need to calculate. I know it's going to be half of 9,000. So that's 4,500. So the total area is then 9 plus 4.5, that's 13.5. 13.5 kilojoules. And that is my exact, not even an estimate, exact energy transferred. So, well, this is a good estimate, isn't it? So my correct answer is C. A length of wire is connected into an electric circuit. The current in the wire is measured. Which change on its own could increase the current in the wire? And the reason, this is a very easy question, but I want to focus on something else. How I imagine current in this wire, especially resistivity problems where they're talking about the radius and the resistivity, what I try to think is that there's a road. Yeah, I don't do any calculations or look at the equation. Let's say there's a road and there's traffic on the road, so some cars on the road, the car on the road, right? So with change to the road or the wire could increase the current in the wire, could increase the flow of traffic, right? And increase in the length of wire, the longer this gets, doesn't really change how many cars go through from a certain point, which is essentially my current. So A is out. If I increase the radius of the wire, if the road is wider, can it carry more traffic at a time? Of course, that's what we all have dreamed about. Whoever's in a urban area, right? So that's true, and we're more or less done. But let's take away our analogy and let's take it further. An increase in the resistance of the wire. Well, if the road was of poor quality, that's adding resistance, or maybe there's a roadblock. So that's probably a better example. There's a roadblock, so there's a resistance. There would be a hindrance to traffic flow. So that's bad. And the last one, an increase in the resistivity. So if the quality of the road depreciated, right, the ability for it to carry more and more cars, or like, would decrease. So it would just backfire. You could only transfer less and less cars. So this is also out. Won't help the traffic. And our correct answer is just B. All right, this is the same question that I'm going to answer in terms of our road analogy, which we solved earlier, right? So the diagram shows the network resistance. Each resistor has a resistance R. So if a car is going from here to here, it's experiencing exact resistance R, right? Now for the other two, we can calculate it and it should be easy, but let's try doing it without it. So it's R, and over here, so what's happening is I have a resistor, so it's a road, but now I have two roads. So here's one path, here's another path. So essentially I am doubling the road or the car's ability. So whatever cars can flow here or current can flow here, it can also flow here. So I'm multiplying the flow rate by 2, essentially with 2, right? So the resistance is gone down. The set over here, the resistance is gone down by half. So the resistance over here is R over 2. And for the third one, the same logic. There are 3 times the current that can flow over here. So it's gonna be R over 3. So that's 1 plus 1 over 2 plus 1 over 3, right? Which is going to be, I think, let's do 6 as the common denominator, right? 6, so we have 6 plus 3 plus 2, 6, 7, 8, 9, 10, 11. 11 R over 6. Our answer is now C. Don't even have to pick up a calculator.